Hi, I thought I'd start this lesson by sharing one of my holiday photographs with you. This is a picture taken in the north of Scotland last year, and it shows a very famous um, exposure of rock by the side of a road in a place called Laxford in the far, far north of Scotland. Now, the reason this place is so interesting is because it tells us a lot about what was happening um, to this part of Britain a very long time ago. Some of the rocks you're looking at here are some of the oldest rocks in Britain, about 3,000 million years old. The youngest rock that you can see here is 1,700 million years old. Despite the fact they're so old, we can actually work out something about their age. Let's zoom in a little bit here onto that part of the outcrop. If we look at these rocks here, you'll see there's a pound coin for scale. We can see there are two different types of rock. Let me just show you where they are. And we've got gneiss and we've got granite. So we've got a metamorphic rock with an igneous rock. Now we can work out the relative age of these rocks. The granite, you can see, is cutting through the gneiss. That means the granite must be younger than the gneiss. Also, the gneiss has been metamorphosed. It's been put under a lot of heat and pressure. The granite hasn't. So we can work out the relative age using this idea of a cross-cutting relationship. It's an idea that I introduced back in the field trip around school when we were looking at the lines being painted on the mugger pitch. So what I want you to do is to actually have a go at applying this. I've given you on page 16 of your booklet a block diagram like this. Each of the features on this have been given a letter. What I'd like you to do is I'd like you to work out the age of these individual events. Remember, the oldest is at the bottom, the youngest is at the top. Can we also identify what type of event it is? What type of thing is being shown by each of these letters? So press pause now and have a go at that. Okay, let's have a look with what you've come up with. So this was the block diagram. We start at the bottom, and the oldest thing there is H, where we've got perhaps a series of sedimentary rocks that have been deposited and folded. They've been bent by pressure acting on the rock. The next thing then is G. G is a fault, it's a break in the rocks. And we know that G must be younger than H because that break has moved the rocks of H. So H had to exist before that fault. The next thing then is D. D is the intrusion of a Pluton. And we can tell D is younger than G because you'll see that D cuts across the fault at G. The fault hasn't broken the rocks at D. The next thing then is C. C is erosion of the sediments to form an unconformity. And you can see that D has been eroded. The next thing then is A. So we get deposition of beds above to form that unconformity. Because you'll see they cut across all the things that are below A on that list. The next thing then is B. B is a dike intruded into the rocks. It cuts through the rocks of H, D, A, cuts through the fault at G, the unconformity at C. But it doesn't cut through F. So F must have formed after the intrusion of the dike. And finally then, we've got E, which is another fault, and E cuts all the older beds. So that's our sequence of events. And we can unpick this just by applying logic. Which event cuts across another one? And if it cuts across, it must be younger. Now, if you had to go at the digging deeper, we've got a very small scale exposure here of a few igneous intrusions. Oldest thing is C there, everything cuts through it. Followed by A, which cuts through C. D, which cuts through A but not B. And then finally B that cuts through everything else. So that's the law of cross-cutting relationships. The final thing we need to think about is what we call the law of included fragments. Now, included fragments tell us that if we find fragments or clasts within a sedimentary rock, they've got to be made of an older rock. They must have existed to be eroded, to be deposited in the younger rock. Remember, we looked at the pebbles that we find in the wall of the canteen. Okay, let's have a go at applying this. In fact, let's put everything together. So this is a field sketch of an outcrop of rock. We've got lots of different things going on here. What I'd like you to do is have a go at question 11 on page 17 of your booklets. Okay? Can you put these things in order, and can you label the geological features that you can see? Okay? Start with 1 as the oldest and keep on going. Okay? Have a go at that. Press pause now. Okay, let's see what we've come up with for this. This is fairly typical of the type of question you might get at GCSE. So, the oldest rock here is schist. It's regionally metamorphosed, so it must be older than all the other unmetamorphosed rocks that we can see around it. We can also see there's an erosive surface there, so there's an unconformity between the schist and the limestone. Those two rocks can't form together, so it's a heterolithic unconformity. The next youngest is limestone, sitting on top of the schist, but in the bottom of the sequence. So we've got a application of superposition, which also tells us then that mudstone must be younger than the limestone. We now need to think carefully, though, about the igneous rock. We've got the dolerite forming a dike, cutting through the country rock there. The basalt then, if we look carefully at that, we've got a couple of bits of evidence there that it's perhaps slightly different. Basalt is finer grained than dolerite, so it's cooled more quickly. Also, if we look at the chilled margin, or the baked margins, I beg your pardon, we can see that we've only got one baked margin at the base of the basalt. And on the top surface of the basalt, we've got a weathered surface, telling us that that basalt must have been exposed. So that basalt is going to be a lava flow. So that's got to be older than the shale that sits above it. The final bed is the sandstone. And we can tell the sandstone must be younger than the shale because there are included fragments of the shale within the sandstone. And there we've got some of the other features that we can see, including a fault there that must be actually the youngest thing in this outcrop because it's affected all the other rocks. Okay, so to conclude, we can apply each of these principles: superposition, unconformities, cross-cutting relationships, included fragments, correlation of fossils, all together to make really good interpretations of the geological history of a place. Just by careful observation and applying these logical ideas, these logical rules of relative dating. Now that's a really useful, really important technique for a geologist. But the next question we need to ask is exactly how old are these things? That's something we're going to try and start to answer in the next lesson. I'll see you then.